Today we will discuss on vector space. First, what is meant by vector space? If all the exams are satisfied by all objects vector u, vector v, vector w in capital V, and for all scalars k and l, then capital V is called vector space. There are three exams. First one is closure exams. Second one is addition exams. Third one is multiplication exams. These three exams are satisfied by all objects vector u, vector v, vector w in capital V, and for all scalars k and l, then capital V is called vector space. Definition of linear combinations and spanning. Let V be a vector space. This means satisfied all exams. Elements of vector space are called vectors. So, therefore, consider vector v1, vector v2, vector v3 and so on, vector vr. Be a vectors in capital V. An element u in V of the form vector u is equal to k1 v1 vector plus k2 v2 vector plus and so on plus kr vr vector, where k1, k2, and so on, kr are scalars, is called linear combination of the vectors. Element u in V can be written in this form k1 v1 vector plus k2 v2 vector plus and so on kr vr vector, that is u is linear combination of the vector v1 v2 v3 v4 v5 v6 and so on kr. We will see example of linear combination. Let vector v1 is equal to open interval 1, 2, 3 and vector v2 is equal to open interval 0, -1, 2 be a vectors in R cube set of real number in triple orders. We have to show that open interval -1, -4, 1 is linear combination of vector v1 and vector v2. That is, vector u is equal to open interval -1, -4, 1 is linear combination of vector v1 and vector v2. Solution of example. In order to show that vector u is equal to open interval -1, -4, 1 is linear combination of vector v1 and v2, there must be scalars k1 and k2. Vector u can be written as k1 v1 vector plus k2 v2 vector. Therefore, vector u is equal to open interval -1, -4, 1 is equal to k1 written as it is. Vector v1 is open interval 1, 2, 3 plus k2 written as it is. Vector v2 is open interval 0, -1, 2 is equal to multiply by scalar k1 to vector v1. So, we get k1 into 1 is k1, 2 into k1 is 2k1, 3 into k1 is 3k1 plus multiply by scalar k2 to v2 vector. We get open interval 0 into k2 is 0k2, -1 into k2 is -k2, 2 into k2 is 2k2. Then addition of this vector, we get k1 plus 0k2, 2k1 minus k2, 3k1 plus 2k2. Comparing left hand side and right hand side, we get k1 is equal to -1, 2k1 minus k2 is equal to -4, 3k1 plus 2k2 is equal to 1. We get 3 equations. After solving this system, we get value of k1 is -1 and value of k2 is 2, which satisfy all the above 3 equations. So, vector u is equal to k1 v1 vector plus k2 v2 vector. If we put value of k1 is equal to -1 and k2 is equal to 2, we get vector u is equal to -1, 4, 1 is equal to -1 into v1 vector plus 2 into v2 vector. Hence, u is linear combination of vector v1 and v2. When u is linear combination of vector v1 and v2, if scalars are satisfied above 3 equations, then we use linear combination of vector v1 and v2. Next topic is subspace. What is meant by subspace? Capital W is a subspace if itself vector space under the given addition and scalar multiplication defined on vector space V. So, capital W is subspace of V. Important theorem on subspace. Let capital W is a subspace of V if the following conditions hold. First condition is capital W is non-empty. Second condition is addition of to any vector is also contained in W for any vector u and vector v in capital W. Third condition is scalar multiplication of vector is also contained in W for any vector u in W and for any scalar k. If the three conditions satisfy, therefore capital W is subspace of vector space V. Most important result. Let V be a vector space. Consider two subspace capital W1 and capital W2. Their intersection capital W1 and capital W2 is also subspace of V. What is meant by subspace? It is closed under addition and scalar multiplication. That is, if the three conditions hold, then capital W is subspace of V. First condition is capital W is non-empty. Second condition is addition of two vector is also contained in W. Third condition is scalar multiplication of vector is also contained in W. Therefore, capital W is subspace of V. Solution of this result. Let x and y be any two vectors. This vector is also belongs to intersection of capital W1 and capital W2. That is, what is meant by intersection? Set of common elements, that is x and y is also contained in W1 and x and y is also contained in W2. But given capital W1 and capital W2 are subspace, it is under addition and scalar multiplication, that is x plus y contained in W1 and also x plus y is also contained in W2. Therefore, W1 and W2 are subspace of vector space V. That is, x plus y is also contained in W1 and x plus y is also contained in W2. Therefore, x plus y is belongs to intersection of two subspace capital W1 and capital W2. Also for any scalar k, capital W1, capital W2 being subspace of A. That is, it is scalar multiplication. That is, kx is also contained in W1 and kx is also contained in W because capital W1, W2 being subspace of V, that is closed under addition and scalar multiplication of vector space V. That is showing that kx is also contain intersection of capital W1 and W2. Hence, intersection of W1, W2 is closed under addition and scalar multiplication. That is, intersection of W1 and W2 is subspace of V because it is closed under addition and scalar multiplication. That is, x plus y belongs to W1 intersection W2 and kx1 belongs to W1 intersection W2. Hence, W1, W2 is subspace of vector space V. Next, most important topic is linear span. What is linear span? Definition of linear span. Let V be a vector space. Consider set S, set of vectors, vector V1, vector V2, vector V3 and so on, vector Vr be the set of vectors in capital V vector space. Then set of all linear combinations of the vectors V1 vector, V2 vector and so on Vr vector is called linear span of this set capital S. It is denoted by L of S or lin S. Thus, L of S is set of all linear combinations of the vector V1, V2 and so on Vr, where K1, K2 are scalars. Last and most important theorem on linear span. Consider set S, set of vectors, vector V1, vector V2, vector V3 and so on, vector Vr be a set of vectors in vector space V. Then we have to show that L of S means linear span is subspace of V. Solution of this theorem is, in order to show that L of S is subspace of V, that is, L of S is closed under addition and scalar multiplication. That is, we have to prove that vector u plus vector v is also belongs to L of S and scalar multiplication ku vector is also belongs to L of S. Then L of S is subspace of V. Consider two vectors, vector u and v belongs to L of S. Vector elements of L of S is also linear combination of vector v1, v2 and so on vr. That is, vector u is equal to k1 v1 vector plus k2 v2 vector plus and so on kr vr vector, and vector v is equal to c1 v1 vector plus c2 v2 vector plus and so on cr vr vectors. K1 k2 kr and c1 c2 cr are scalars. Then Addition of these two vectors is vector u is k1 v1 plus k2 v2 plus and so on krvr plus vector v is c1 v1 plus c2 v2 plus and so on crvr. Then we can write k1 plus c1 into v1 plus k2 plus c2 into v2 plus and so on kr plus cr into vr. Elements of vector u plus v is linear combination of vector v1, v2 and so on vr. Scalar multiplication also element of this vector is linear combination of vector v1, v2 and so on vr. Thus, vector u plus v and ku vector are linear combination of the vector v1, v2 and so on vr. Vector u plus v and ku vector is belongs to L of S, is also member of linear combination of these vectors vector v1, v2 and so on vr. These also members of L of S. Therefore, L of S is closed under addition and scalar multiplication. Thank you.